Welcome to my first video in this series of videos for the mechanical engineering program at BCIT. Basically, if you're new to this program, well, obviously you are. If you're watching this for the first time, I'll be just making videos of concepts and problems that I think are very important and are might be confusing for a lot of people, and I'll be showing ones that were confusing to me, and if you need any help, you can just watch them and stuff. So without further ado, I don't want to waste time, so we are going to be learning about right now about Young's modulus, which we learn in materials, so material sciences or chemical sciences. Okay, Young's modulus. Now bear with me, I have a mouse, so I can't really draw that well, but I guess it's fine for now. Young's modulus is all about the concept of stress over strain. Which equals modulus of elasticity. That's the concept of Young's modulus. That the modulus of elasticity is the stress over strain, or you can find all these different variables, and you can find E times strain equals stress, or stress over E equals strain. Just a matter of rearranging the variables. Okay, so what it means is that at the beginning, what the modulus of elasticity is judges how easy is it for me to pull with a force on an object with a length, we'll call this LO for the original length, and over an area. So this area, this square cross-sectional area, which is A. Now this block is fixed. Let's fix it to this square, whatever, rectangle. Let's fix it over here. So this whole block can't move, but it can stretch. So we attach something to apply a force to this block, and it will move. It will not move. It will stretch. So it will get bigger. I'm not drawing this properly, but it'll get bigger. Then the length will increase, which is, let's say this right here. I'm just going to point that there is a change in length, or delta L. That is delta L. So if I apply a force, this thing's going to stretch. This piece of metal or whatever is going to stretch a certain length, which is delta L. And these are the four variables you need to calculate the modulus of elasticity, because stress is force divided by area. Strain, let's equal that. Strain is change in length divided by original length. And that is your equation for Young's modulus, to find out the modulus of elasticity. Now, the units for force, area, and length are basically newtons. For metric, I'm going to be dealing with metric right now. Newtons per meter squared divided by meters divided by meters per meters, which basically meters divided by meters, that cancels out, and strain is unitless. That means that E is measured, this elastic modulus is measured in newtons per meter squared, because the meters at the bottom cancel out, and it's unitless. So you'll have a number, because it's a ratio of two numbers, and it has no units. Just the strain, though. So basically, now that we have our units and what we write down, we can calculate. We can find a problem now. But first, I will tell you about elastic and plastic deformation. Elastic deformation is like a rubber band. It happens when you pull on something, it gets a bit longer, you let go, and it comes back to being shorter. And plastic deformation is basically permanent deformation, which is basically when you pull on an object so hard that it stretches, and then when you let go, it won't come back to its original length. So that's what you got to remember. Now, basically, this helps a lot in material sciences because you can imagine that you want to build a bridge with certain forces on it, and the materials you're using, you know the elastic modulus of the materials, but you want to know how much it'll stretch or if it'll break, basically. So, okay, so I guess that's all I could say for that about the equation. Now, the units are this is metric units. You can also put them into standard units, which are pounds per foot squared, divided by feet per feet, which is nothing, right? Okay, E is measured in pascals, but we normally measure it in gigapascals because the Pascal number is really high. So you measure in gigapascals, which is 10 to the power of 9 pascals, which you'll see soon. Okay, now I'm going to go on to the example, which I have gotten. Oops. Okay. And the example, basically, let's go all the way to that. Okay. Now, what we have here is I'll read it. A metal bar 116 millimeters long and having a square cross section with a width of 19 millimeters is pulled under a tensile load of 74,500 newtons, which causes an elongation of 0.10 millimeters. Assuming that the deformation is entirely elastic, calculate the elastic modulus in gigapascals of the metal. Now, what do we know? The variables that we know is that it is 116 millimeters long, so we want to find that. So we have 116 millimeters long, so LO will be our original. Now right away let's convert these to meters, so we don't have millimeters everywhere. So 116 millimeters is 0.0116 meters. Is it? Nope. No, my bad, sorry. It's actually 0.116 meters. Because that's 11.6 centimeters, which is that. Okay, so sorry. It has a square cross section with width. It's a square, so width and length are 19 millimeters. So let's just calculate the area right now with meters. So 0.019 meters squared. Okay, which turns out, let me calculate this. 0.019 squared equals 0.0000361 meters. Sorry, this was supposed to be millimeters. Sorry. Anyways. Okay. So now we have millimeters squared. And we have meters squared. Okay? Now the load, the force, so we're getting closer to each of the variables. The force is 74,500 newtons. That's all we have to do with no conversion. And the change in length causes an elongation of 0.1 millimeters. So that is 0.0. So we're in the tens place of the centimeters, or the hundreds place of millimeters, tens place of the millimeters, ones place of the millimeters, 0.1's place of the meters right here, millimeters. So that many meters, that's how many meters it is of elongation, because we're changing this value to meters. Assuming that it's entirely elastic, calculate the elastic modulus in GPa of the metal. So let us go down a bit more. So we want to find the GPA. So we write down the basic equation. E equals force divided by area over change in length divided by original length. So let's plug these in. 74,500 newtons. Sorry, it looks like W, but newtons. Divided by area, which was this number. I don't want to write it out, so this number is the area right there. Area. Divide all that by change in length, which is 0.0001 meters, divided by, what was the normal length? Original length, 0.116 meters. So now I'm going to calculate all this, so give me a second. 74,500 divided by 0.000361 divided by 0.0001 divided by 0.116. And now we have a value which is 2.4, or let's have more significant figures. 2.394 times 10 to the 11 pascals. So this is in PA, pascals, which is in Newton meters. Newton divided by Newton per meter squared, actually, yeah. Newton per meter squared. So that's how much pascals. We want to change to gigapascals. So what we want to do is take this decimal, move it one time. This number goes down to 10. Move it another time. This number goes down to 9. So now we're at 9. So we rewrite 239.4 times 10 to the power of 9 giga. No, actually, whoops, not 10 to the power of 9, because 10 to the power of 9 is a gigapascal. So that is how many gigapascals we have. And that is your answer to the problem. See, it's not very difficult to find these. It's a pretty simple concept, and just remember to switch your units from millimeters to meters, and remember to convert back to gigapascals if it asks for it. And that's it for the video. If you have any questions, please leave comments, and I'll be probably doing some more videos on different subjects.